All right. Okay, so I'm going to review a little bit about what we did last time on chapter 7. So the plan for today is we're going to review a tiny bit of the stuff from chapter 7 on hypothesis tests. I'll review the problem that we did Wednesday just to make sure that we haven't forgotten it. And that was a two-tailed problem, a two-tailed hypothesis test that we did last time. Today, I'll give you a new example, which is a one-tailed test. So we'll review the two-tailed test, and we'll do a new one-tailed test today. And then we will start chapter 8. When we'll get through the confidence interval stuff, I believe, pretty quickly, and that'll be it. So hypothesis testing will finish, and then we'll get through the confidence interval section of the next chapter. So for the hypothesis test example that we did last time, it was a two-tailed test, as I mentioned. The question that was being asked, and it's mentioned here, would giving people some math drug, would that influence their performance on a math test? And so the population was the average score of the population was 80. And remember, these are people that scored, these are people that didn't take math drugs. These are just all the students at like KU or whatever that just take a math test without taking math drug. And they got the average score is 80 with a standard deviation of 20. The question is giving math drug, does that change people's performance on the math test? Would that make their performance differ relative to 80? So we sampled 25 students, randomly sampled 25 students from the population, and then we gave them math drug, and then they took the test, and then the score for them was 89. And the question that we're asking, the essential question we're asking here for the z-test is that score of 89, is it significantly different than 80? So we did this stuff last time. We'll kind of review quickly. So anytime you're doing a hypothesis test, at least in this class, we're supposed to come up with the null hypothesis and the research or alternative hypothesis. And we did that last time. So the null hypothesis basically predicts there's no effect. The null hypothesis from last Wednesday was the mean score of people that take math drug is 80. Remember, the null hypothesis says the treatment, math drug, has no influence. If the treatment has no influence on people's score, then they're still going to have around an 80 even after taking math drugs. That's the null hypothesis. People who take a math drug, their score is still going to be around 80. That's the null hypothesis, predicting no effect. The alternative hypothesis, or the research hypothesis, simply predicts that there is an effect, that math drug will either increase people's score on the math test or it will reduce people's score on the math test. So this is a two-tailed test, and I've mentioned that you can always tell how many tails a hypothesis test is by looking at the alternative hypothesis. And I mentioned last time that if I say mu just with math drug does not equal 80, that really kind of means two things. It can mean two different things. What are those two things? You can kind of unpack mu does not equal 80 into two things. What are those two things that you can unpack this into? I'll give you a clue. It's the two tails of our distribution. Mu does not equal 80 can be unpacked into meaning two different little subcomponents. What are those subcomponents of mu does not equal 80?
Greater than or less than?
Yes, that's right. Basically, greater than or less than 80. You say the whole sentence. Like it means that mu with math drug is greater than 80, or mu with math drug is less than 80. Both of those things would satisfy the statement mu does not equal 80. If we give people math drug and it causes their performance to be significantly greater than 80, then that supports our research or alternative hypothesis. If we give people math drug and it happens to significantly reduce their scores and make it less than 80, then that would also support our research hypothesis. That would also support our alternative hypothesis. So with the two-tailed tests, there are two different things that can happen that will make us reject the null hypothesis, that will make us accept the alternative hypothesis. One, you give them the treatment and that causes their scores to increase dramatically. That's one side of the tail. You can also give them the treatment which will decrease their scores dramatically. That would also that would be on the other side of the tail. Either of those situations, either of those two tails would be taken as support for the research. That is the alternative hypothesis. So you can look at that research hypothesis. You can tell it's two tails because mu does not equal 80. There's two things that means. Mu is greater than 80 or mu is less than 80. Those are the two tails. Here's a way of kind of looking at this visually. The population mean of 80 would be here in the center, where we calculated the z-score that corresponds to our sample mean. And if that z-score falls in either of these two blue regions, then we conclude that there is a significant effect that we should reject the null hypothesis. What are those? I gave you a name for those blue regions, and so does your textbook. Does anyone remember what is the name for those blue regions? The blue regions where if the z-score corresponding to your sample mean falls in either of those two blue regions, then you reject the null hypothesis. That is, you conclude that there is a significant difference. Does anyone remember the name of those blue regions?
Is it alpha?
The alpha is very important to determining the amount of area that falls in those two regions. So you're getting warm. That's alpha is an incredibly relevant aspect of what those two blue regions are, though that's not technically the name of those two blue regions. I'll give you a clue. It starts with a C.
The critical points?
Yes, critical regions. The critical points technically are these exact things. Like the critical boundary are these vertical lines right here. Those are z-scores that mark the beginning of the critical region. So there's the critical boundary or the critical points. And then outside of those critical boundaries, outside of those critical points is the critical region. So the blue things are the critical regions, where those vertical lines right there, those are z-scores that mark the critical points or the critical boundaries. So good. And so, yeah, talking about alpha, alpha commonly is in psychology. Would you guys remember, what did I say the most common alpha in psychology is? Does anyone remember? The alpha level, which is commonly used in psychology, is 5% or 0.05. And someone just mentioned correctly that these blue regions are related to this concept of alpha. What alpha is it's basically the total percentage of the distribution which falls in these critical regions right here. So if alpha equals 5%, if alpha equals 0.05, then the total amount of area that is blue equals 5%. We have these two tails here, right here. In this example, we have two tails. The total amount of area in those two tails is 5%, which means how much area is in just one of those tails?
2.5.
Yes, 2.5% is correct. If alpha equals 0.05, if alpha equals 5%, and we're doing a two-tailed test, basically what we do is we take that 5% and we equally distribute it among those two tails. 2.5% goes in the left tail, 2.5% goes in the right tail. So we talked about the critical boundaries just a second ago in the critical region. The critical boundary that we're going to care most about in this class will be this negative and positive 1.96 plus or minus 1.96. This is probably the most important critical Z value. This is the Z score, which marks the boundary into the critical region when you have a two-tailed test where alpha equals 0.05. You have two tails. Alpha equals 5%. The z-score of negative 1.96 marks the point in the distribution where 2.5% of the area lies to the left of that z-score, and 2.5% of the area lies to the right of positive 1.96. So the z-score of plus or minus 1.96 is really important because this marks the critical boundary for the alpha level, which is most common in psychology. Alpha 5%, 0.05. The z-score plus or minus 1.96 marks the point along the distribution where 2.5% of the area is in the left tail and 2.5% of the area is in the right tail. So we'll be using this 1.96 a lot in this class because in psychology we care a lot about alpha equals 0.05, and this is the critical z-score for alpha equals 0.05 when you're doing a two-tailed test.
I have a question about that.
Yeah.
How do you how do you determine the 1.96?
Yeah, so if
In
you
the book they have a Z table. It's like an appendix B or something they keep talking about when you read the chapter. And if you find like your percentage, 37.5 correlates with the 1.96 somehow.
Yeah, I don't think correlates is the word that they use, but yes, they do. So this is a great question. What I would suggest, someone's got their microphone on. If you could turn that off for a second, or turn it off, please. Yeah, so this is a good question. If you look up -1.9, I would use the z-table that I gave you. That's the one that I taught you to use. You can also use the one in the book, though it's slightly different, in my opinion, harder to use. The one that I gave you, I think, is easier to use. So I would use the z-table that I gave you in the slides, and I also sent you an email with my z-table in it. If you look up on your z-table, the percentile that corresponds to the z-score of -1.96. Remember, what does percentile mean?
Area to the left.
Area to the left. So if you look up the z-score of -1.96, and then you look up the percentile, that is, if you look up the value that corresponds to -1.96 in the z-table that I gave you, it's going to say 0.025 or 2.5%. So this number, -1.96, if you use the z-table and you find this number, the amount of area to the left of that number is going to be 2.5%. A related question, if you use my z-table and you look up 1.96, what is the percentile for z-score of 1.96? So remember, when I ask you percentile, I'm asking you how much area is to the left. So if you looked up 1.96 in the z-table that I gave you, how much area is going to be to the left of that number?
97.5.
97.5%. And if you take 100 minus 97.5, you get 2.5% right here. So if you look up the z-table, and I strongly suggest you do this to help yourself understand this, because it's true. This stuff is all related to the z-table. Look up -1.96. You're going to find that 2.5% of the area is to the left of this z-score right here. If you look up +1.96, you're going to find that 97.5% of the area, that's basically all of this, that's 97.5%. 97.5% lies to the left of this number, which means 2.5% lies to the right of that number. This is all derived from the z-table. Does that help answer that student's question? Let's hopefully so. Okay, so let's continue on. Okay, so yes, let's just go through the problem that we did last time. So let's see. Yeah, here's where we did our work. So what we want to do, we're gonna calculate we already know our sample mean is 89. We want to calculate the z-score that corresponds to that score of 89. And what we want to know is that z-score of 89, is it in the critical region or is it not in the critical region? If it's in any of this middle part, if our z-score of 89, the z-score that corresponds to our mean of 89, if it's in this middle part, we conclude there's no significant difference. Math drug didn't do anything. We accept the null hypothesis. If we convert our 89 into a z-score, and then we find that z-score is greater than 1.96, that is, that z-score is greater than 1.96, it's in the critical region, then we reject the null hypothesis. We conclude that math drug has a significant effect and that it affects people's performance on the math test. So here's the work that we did last time. This is the Z formula that we used. We're using this Z formula to convert the sample mean of 89, that's the score of people when they took math drug on the math test. We're going to convert that score to the Z-score, and that's what's shown right here. Someone remind me, what is this thing right here? What is the symbol? What is the name of this thing? Like, what is this sigma sub m? Anyone remember what that means?
The standard error.
Yes, thank you. It's not the standard deviation. Good. It's the standard error. And the standard error has these two components right here. Something divided by something else. What are these two things right here? This is the standard error. You're dividing one thing by the other. What are these two things? What are these numbers right here?
The numerator is the standard deviation and the denominator is the square root of n, or the sample size.
Good. Yeah. So just looking at this bottom thing right here, this overall thing is the denominator. If we look at the top part, or the numerator right here, this is 20 comes from the standard deviation of the population. So this is the standard deviation of the population divided by the square root of our sample size, which was 25. So this whole thing, the standard error, once again, is the population standard deviation divided by the square root of the sample size. So 20 divided by the square root of 25 gives us 4. This 89 right here is the sample mean. This 80 right here is the population mean. When we did all that, when we crunched the numbers, we got our z-score of 2.25. The z-score corresponds to the sample mean of 89 right there. And so the question is this 2.25, is it greater than our critical z? Our critical z is plus or minus 1.96. We're on the positive side. So really the question is 2.25 bigger than 1.96? And the answer is yes, it is. 2.25 is greater than 1.96. Therefore, we reject the null hypothesis. So kind of visualizing what that is, 1.96 is our critical boundary on this side. 2.25, which is the z-score that corresponds to our sample mean of 89, would be around right there. 2.25 would be around right there. Clearly, that's in the critical region. Therefore, we would reject the null hypothesis. Okay, so that was an example of a two-tailed test. So now we're going to do an example of a one-tailed test. A one-tailed test is, in a one-tailed test, basically you have, and your research hypothesis predicts that the treatment can only have one type of an effect. And the example that we just did, our research hypothesis had two potential effects that could occur. The research hypothesis in the previous example that we just did said, we give people math drug, and it can do one of two things. It can either increase people's performance on the math test, or it might decrease people's performance on the math test. But there are some situations in science in which you are so confident that the treatment could only have one possible direction of influence. It could either increase or decrease, but it couldn't possibly do both, that you'd use what's known as a one-tailed test. You use a one-tailed test when you are so confident that the treatment can only have one direction of effect. And that's what's shown here. If you are very, very positive that math drug could the only thing it could possibly do is increase people's performance on the math test, or have no effect at all, what you do is you take that 5% area, you take alpha, 0.05 or 5%, and you move all of that alpha into one tail only. Here, it's shown in this one tail, right here. You put all of the alpha into one tail right here, all 5% goes into one tail, and then you only have one critical region when you're doing a one-tail test. Instead of you having two critical regions, one which is less than the population mean and one which is greater than the population mean, when you're doing a one-tail test, you only have one critical region, and it is either greater than or less than the population mean. In the depiction here, we have a one-tailed test where we're basically, the research hypothesis says the only thing that could possibly happen is the treatment will improve people's performance. It will increase the mean. And when you do a one-tailed test, once again, you're taking all 5% of the alpha and you're shoving it into one tail. Instead of dividing the alpha into the two tails, in which case you have 2.5% on one side, 2.5% on the other, you're taking that 5% and you're putting it all in one tail. And so here's an example of a one-tailed test. And it will kind of help illustrate, I think, like why you would ever use a one-tailed test. So we'll go through this, and we'll do this entire example of a one-tailed test. So our example here is, and this comes from, by the way, the book, chapter 7. So our population mean here is 247. So the 247, which is shown on this top line, this is the average amount of calories that people across all American cities consume calories when they visit a Starbucks. The average amount of calories at a Starbucks across all people in the United States, given any city in the United States, is 247 calories. But for our study, we're interested in a particular question. How many calories do people in New York consume when they go to a Starbucks? And the reason why this is a theoretically interesting question, at least according to the textbook, is because New York is the only city, or the only city where a law requires that the amount of calories for each item on the menu be posted on the menu. And so the question is does knowing how many calories a food item has by looking at the menu, does this influence the amount of calories that people end up eating at Starbucks? But if you think about this question, there's really only one potential direction, at least according to the assumptions of the textbook, where knowing the amount of calories could only really influence your performance and your amount of calories you consume in one way. It could reduce the amount of calories. The idea here is, if you know how many calories you're going to eat, then the only thing that could do is decrease the amount of calories that you would possibly eat. Because most people, want to watch the calories, don't want to overeat. If you actually know how much calories you're eating and you can see it on the menu, the idea here is that the only thing that can really do is decrease the amount of calories that you would possibly eat. And so we'll talk about how this is a one-tailed hypothesis. We would predict that knowing the amount of calories on each menu item has, that could reduce the amount of calories that you would eat, but it could not possibly increase. That's the assumption. Knowing the amount of calories of each item can decrease the amount of calories on average people eat, but there's no way that it could possibly increase the amount of calories that people eat. So this will be an example of a one-tailed test, because our research hypothesis is that, and we'll jump down to our research hypothesis. Our research hypothesis is that the mean amount of calories that people in New York eat, remember people in New York know how many calories each item on the menu has, that will be less than 247. You can tell that this research hypothesis has only one tail because it only has one inequality. Remember when we did the two-tailed hypothesis test just a second ago, there was a left tail, which was mu is less than something, and there was a right tail, which is mu is greater than something. Those are the two tails for the research hypothesis a second ago. In this example, the research hypothesis only has one tail, which is why there's only one inequality here. And then the null hypothesis, therefore, will be all other possibilities. Null hypothesis is, remember the null hypothesis says there's no effect at all. Knowing the calories is not going to have an effect, but there's kind of two things that count as satisfying the null hypothesis when you're doing a one-tailed test. Either one, the mean amount of calories consumed equals 247. That's what the line down there. So either the mean amount of calories equals 247, or the mean amount of calories is greater than 247. But if we're doing a one-tailed test, even if it turns out that when we measure the amount of calories that people consume at Starbucks in New York, if it turns out that that number is drastically more than 247, because our hypothesis was a one-tailed test, because it was directional, we actually count that as satisfying the null hypothesis. So if we calculate the amount of calories that people ate in New York and it turns out to be 280, we would actually say that counts as the null hypothesis, because we did not hypothesize that it would be possible that the amount of calories could actually increase. So there's kind of two parts of the null hypothesis if you're doing a one-tailed test. Mu equals 247, or in this case, mu would be greater than 247. If either of those happens, we say there's no effect. The amount of calories, or knowing how many calories that are on the menu, that doesn't affect the amount of calories they consume. So let's look at the actual data that we collected. When we actually collected data from calories consumed in people from New York, we found that the average calories consumed was 232. That was based on a sample size of 1,000 New Yorkers. The standard deviation of our original population, so the standard deviation is connected to this mu right here. The average amount of calories consumed across all cities was 247, with the standard deviation of 201. And once again, our research hypothesis, we're predicting, okay, the only thing that could possibly happen is when people know the amount of calories on the menu, that could only decrease the amount of calories that they end up eating. So our alternative or research hypothesis is that the average amount of calories that people in New York consume is less than 247. So we're doing a one-tailed test. Our alpha equals 0.05. And so now our critical Z is going to be negative 1.65. This is just something to memorize. If we use this critical Z, if you look up negative 1.65 on the Z table, there's going to be 5% of the area. The percentile for this is 5%. 5% of the area is to the left of this Z-score of negative 1.65. The question we have is, when we convert this score, 232 calories, to a Z-score, is it going to fall into our critical region? And so I had to draw this one by hand. Here's kind of the critical region right here for this hypothesis test. Z-score of negative 1.65 right here. This is the critical boundary. The critical region is everything over here. Z-score of Z equals 0. This marks the population mean of 247. What we want to know is when we convert our Z-score of 232, when we convert our score of 232 into a Z-score, is it going to fall into this critical region, in which case we would reject the null hypothesis? Or is it going to fall into this white area right here, anywhere in this white region, even if it's way over here, you would accept the null hypothesis. If our z-score that we calculate is over here, we reject the null hypothesis. If it's anywhere in the white region, even if it's way over here, we accept the null hypothesis. So here's the math to calculate our z statistic for our sample mean of 232. Once again, we're using this formula right here. This is our sample mean of 232, our population mean of 247. 201 is our population standard deviation. 1,000 is our sample size. We take the square root of that. When we crunch all these numbers with our calculator, we would get a z-score of negative 2.36. Now, I should point out, even before we calculate all of this stuff, we should have known that we would get a negative z-score because our sample mean of 232 is less than our population mean of 247. So we should have known going in that we are going to get a negative z-score, which we do. So, but now what we want to do is we kind of want to see, is this z-score is in the critical region? So going back to our picture right here, our critical boundary is z equals negative 1.65. The z-score that we calculated that corresponds to our sample mean of 232 was negative 2.36, which would be somewhere over here. The critical boundary is negative 1.65. Negative 2.36 would be somewhere over here. So that negative 2.36 is in the critical region. And so someone tell me, would we accept or reject the null hypothesis?
Reject.
We would reject the null hypothesis. The z-score that we calculated is over here in the shaded region. It's in the critical region. Therefore, we would reject the null hypothesis. What we would conclude is that knowing the amount of calories based on what it says in the menu has a significant effect such that it reduces the amount of calories that people consume. And it says right here, people who see calories in the menu in New York ate significantly fewer calories than the rest of the population, people in other cities who did not know the amount of calories on the menu. Any questions or comments about two-tailed versus one-tailed tests before we close the book on chapter 7? All right. So let's move to chapter 8. All right. So this is chapter 8 on confidence intervals, effect size, and statistical power. All we're going to get to today is this. We're going to do an example of a confidence interval. We'll do effect size and statistical power on Wednesday. So a confidence interval is basically two things. It's a combination of two things. One thing is called a point estimate. And for our purposes, the point estimate, it says here, is a mean, but I'll be even more specific. The point estimate for us will always be our sample mean. So we're going to calculate some sample mean. We've done this a bunch of times now. And that is the point estimate, is the sample mean. And you can see the definition of a point estimate. It's a single number or a summary statistic. That single number, just one number, that is used to kind of mark the center of our distribution. Or here they use the language, it estimates a population parameter. But I kind of like it. I kind of prefer, in my mind, this is language is common in textbooks, that the sample mean is an estimate of the population parameter. But I just think of the sample mean as the center of a distribution. That's how I think of it. That's what the point estimate is using the sample mean as the center of a distribution. And I want to point how this is different than what we just did in chapter 7. In chapter 7, every time we made a distribution, and we've looked at a couple of them, the thing that was at the center of the distribution was always the population mean. When we're doing confidence intervals, it's kind of the inverse. We kind of flip-flop things at confidence intervals. We're making confidence intervals. The thing which is in the center of the distribution now is the sample mean. So that's the primary difference between the two, is that the sample mean is the center of the distribution when we're doing confidence intervals, but it's the population mean, which is the center of the distribution when we're doing the hypothesis test technique in chapter 7. So that's point estimates, a single number at the center of the distribution. The interval estimate, the example that I kind of think of to always remember what an interval estimate is, there's a famous example in psychology from 1950s. There's research on the capacity of short-term memory performed by a researcher named Miller. It's kind of a famous study about the magical number 7 plus or minus 2. This researcher said that the average capacity of people, their short-term memory was 7, But that 7 was a point estimate. It was an average number which represented the center of the distribution. But some people were actually higher than 7. So some people you would measure their short-term memory and it was greater than 7. So they would have like a short-term memory ability of 9. Some people you would measure their short-term memory ability and it would be less than 7. They might have like a short-term memory of 5. So the point estimate was 7, but there was an interval on either side of the 7, an interval that was bigger than 7 plus 2, and an interval that was less than 7 minus 2. So that's why Miller said the average short-term memory capacity was 7 plus or minus 2. That plus or minus 2 aspect of this is the interval estimate. It's basically a range of values which are placed over the center of the distribution. Once again, I mentioned the point estimate for us is the sample mean. That marks the center of the distribution. The interval estimate basically is a plus or minus that we put on either side of that sample mean. That is the confidence interval. The interval estimate plus the point estimate basically is the confidence interval. Another common example of confidence intervals comes from political polling data, when you would say that the average approval rating for so-and-so candidate was some number plus or minus a margin of error. Margin of error is another word for interval estimate. It's basically this interval above and interval below the mean, the point estimate, and that kind of represents the center of the distribution. There's a little bit to the left of the point estimate, a little bit to the right. That's the interval is either side of the point estimate. The point estimate plus the interval estimate combined form the confidence interval. So here's some important information about the confidence intervals that we'll be doing in this class. Once again, I've already said, the sample mean will always be the center of our confidence interval. This is different than what we did when we've made distributions before. We've always done it differently. In the distributions before, the thing that was the center of our distribution was always the population mean. For confidence interval, the sample mean is the center. So it's the inverse, kind of changing things up to what we've been doing before. And then there'll be a margin of error to the left of our sample mean, and there'll be a margin of error to the right of our sample mean. That's the interval estimate, the plus or minus aspect of things. And that is, by the way, assuming a two-tailed hypothesis test. Technically, if you were doing a one-tailed hypothesis test, you would only have a margin of error that was either to the right of your sample mean or to the left of your sample mean. Though to my knowledge, based on my reading, your textbook never does that. And these are actually, a one-tailed confidence interval is incredibly uncommon. I don't think I've ever actually seen one. In this class, we will always be dealing with two-tailed confidence intervals. That is, the margin of error is to the right, and there's a margin of error to the left of the sample mean, which forms the center of the distribution. Basically, almost every time in this class that we would be doing a confidence interval, we would be doing a 95% confidence interval. And so let me actually show you what that means. Here's my drawing of a 95% confidence interval. This is using the sample mean. Do I have a question? I hear someone's microphone.
Yeah.
Yeah, go ahead.
I'm confused. Is the margin of error always going to be like 5%?
No, the margin of error is usually going to be, I'm glad you asked the question, but you're like 1 second ahead of me. So just let me explain what I'm about to explain, and I believe it will answer your question, okay? So the margin of error is not always the same thing, but for our class, usually it will be. Usually the margin of error that we will almost always have will be plus or minus 47.5%. That's what we'll use. But I want you to understand why we're using 47.5% on the left and 47.5% on the right. So right here, this is using our example of math drug that we did Wednesday and we kind of reviewed earlier today. When we gave people math drug and then we took their mean performance on the math test, we got a score of 89. So this is our sample mean right here. And then this number right here, this is a z-score of negative 1.96, which, remember, if we use alpha equals 0.05, 2.5% of the area is to the left of a z-score of negative 1.96. 1.9, if we use z-score of 1.96, 2.5% of the area is to the right of that. In this class, we'll almost always be using a confidence interval of 95%. What that means, a confidence interval of 95%, What that means is that 95% of the area is in this white area right here. The area which is not shaded, 95% of the area is there, which means, to answer the question that was just asked, our margin of error to the left would be 47.5. Our margin of error to the right would be 47.5. So you could think of the margin of error is plus or minus 47.5%. Though I think the plus or minus language is a little bit more complicated than just saying, well, what do you get when you add 47.5 plus 47.5?
95.
Yes, 95. So in other words, this is just a 95% confidence interval because 95% of the area is in this white section right here. 2.5% of the area is in this tail, 2.5% in this tail. If you add both tails together, that's 5%, which means 95% of the area is in the center of the distribution. So I would just say that this is a 95% confidence interval centered around the sample mean of 89. Though you could also say that this is 89 plus or minus 47.5%. Though I would just say this is a 95% confidence interval centered around the sample mean of 89. So yeah, we're going to be mostly in this class, we'll be doing 95% confidence intervals. That's the focus of this chapter. In which case the margin of error would be considered 47.5%. And you could use these confidence intervals. Really, mathematically, confidence intervals are exactly the same stuff that we were doing in hypothesis tests in chapter 7. It's just, it's literally the exact, mathematically, it's the exact same stuff that we were doing in chapter 7. It's just, it's just calculations are slightly different. Like the results you get with confidence intervals are the exact same results you get if you're doing the hypothesis technique chapter that we did in chapter 7, the hypothesis testing technique from chapter 7. It's the exact same results, except the mathematics, you use different computations, but mathematically you will get the exact same decision whether you should accept the null hypothesis or reject the null hypothesis when you're doing confidence intervals. So I think the textbook does a slight disservice to you because it makes you think that these things are dramatically different than hypothesis tests. Confidence intervals are the same stuff as hypothesis tests. It's just slightly different perspective. You get the exact same decision whether to accept or reject the null hypothesis. The basic logic, which I'm stating here, I'll kind of just read this. If the population mean falls outside of the interval estimate, that is outside of the confidence interval, then you reject the null hypothesis. So right now, I've just given you a whole bunch of words, and it's a little bit confusing probably until we just do an example. And I really believe the example that we'll do will help clarify a lot of this stuff that I just said right here. So we'll go through the steps of confidence intervals pretty quickly right here. We're going to draw a picture. I've already shown you the picture. Show it to you again, I guess. The sample mean is the center. We have two tails. The center is the center part is 95%. So we draw a picture of a distribution that includes our confidence interval. That is the left tail and the right tail. And anything in between those two tails is the confidence interval. Indicate the bounds of our confidence interval by drawing those markers, the two tails. You could see that in the picture I just showed you. We determine the z statistics that mark those boundaries, the middle 95%. We know that these are the correct answers because, once again, negative 1.96, 2.5% of the area is to the left of this, 2.5% of the area is to the right of this. 2.5 plus 2.5 is 5%, which means the leftover is 95%. 95% of the area is in our confidence interval. The distance, the percentage of here to here is 95%. And so it says here, convert the z statistic back into raw means for each of the CI. This is really the essence of what we're doing for confidence interval. I think the textbook makes it a little bit more complicated than it needs to be. Really what we're doing, the core thing that what we're doing for confidence intervals, once again, we're assuming that the sample mean is the center of our distribution. And we have this z-score right here, and we have this z-score right here. Really all we're doing for confidence intervals is we're transforming this z-score back into an x value. And we're transforming this z-score back into an x value. That literally is the confidence interval. What is this x value right here? What x value corresponds to a z-score of negative 1.96? That's the lower bound of our confidence interval. What is the x value that corresponds to the z-score a positive 1.96. We're going to calculate that X value. That is the upper bound of our confidence interval. So really, this is the core of what we're doing in confidence interval, is just transforming these two z-scores into their corresponding X values. That is the confidence interval. And that's what step 4 is here. And then step 5 is just basically checking your work. Make sure that the answer that you're providing makes sense. So here's the example that we're going to use for our confidence interval right here. This is the exact same example that I showed you earlier from chapter 7, except instead of doing the hypothesis technique from chapter 7, we're going to just make a confidence interval for the exact same example that we did from chapter 7. The population mean was 80. So these are the people that got 80 on the math test when they did not take math drug. The standard deviation was 20. The question is, does giving math drug influence these people's performance? So we took 25 people, we gave them math drug. The sample mean of those 25 people was 89. The standard error that we calculated when we did this hypothesis test earlier was the standard deviation of 20 divided by the square root of the sample size, 25, which gave us 4. When we did this hypothesis test back in chapter 7, we rejected the null hypothesis because the sample mean of 89, the z-score that corresponded to that 2.25, was greater than the critical z of 1.96. 2.25 was greater than 1.96. Therefore, we rejected the null hypothesis. We concluded that giving math drug to people had a significant effect on their math performance such that it increased their math performance. What we're going to do now is we're going to take a confidence interval, which is centered about this sample mean of 89. And once again, we're going to calculate, we're going to transform this z-score right here into the lower bound, an X value. And we're going to transform this z-score right here, 1.96, into the upper bound, which is an X value. And so here is the formula that we're going to be using to do this. I want to point out that the formulas that I'm providing are slightly different than the book. The book and a lot of textbooks are confusing with confidence intervals. I think it's one of the more confusing things the way it's taught in textbooks. And the thing which is confusing about the textbook is it leaves out the word critical. And I think including the word critical is critical, very important, because when we're doing these types of problems, there's two types of z things there's two z-scores that we always have to worry about. There's the z that corresponds to the sample mean, but there's also the critical z. The critical z is that z-score that marks those boundaries. And then the sample z is the z-score that corresponds to our sample mean, which could either fall in the critical region or is not in the critical region. And so it's really important when we're dealing with these things to remember, are we talking about the critical z's or are we talking about the sample z? The book isn't quite clear enough about that as I would like. So my formulas, I added the word critical here because I don't want you to forget that the z's that we're including in these formulas, these are not the sample z's. These are the critical z's. And so if you're doing a 95% confidence interval, assuming 2 tails, the critical z is the z-score that we've been dealing with a lot now, plus or minus 1.96, which you can see I've substituted negative 1.96, that's the negative critical z right here, positive 1.96, that's the critical z right here. These are the z-scores, by the way, to remind you, that mark the boundaries into the critical region. So these are critical z's right here. What is the symbol right here stands for? Sigma sum ib. What does this stand for?
Standard error.
Standard error. And I showed you on the previous slide, or 2 slides ago, the standard error equals 4. We calculated that for this problem previously. So we're going to put in 4 right here and another 4 right here. So we take, for each one, we take negative critical z times the standard error plus our sample mean, which was 89. That's for the lower bound. For the upper bound, we take the positive critical z, 1.96, times our standard error of 4, plus the sample mean, which is once again 89. So you can see how I set things up right here. And then you just do the math. You just work it out. And I want to remind you what we're doing is we're just taking the z-score right here, negative 1.96, and we're basically asking, what x value does this represent? We're taking this positive z-score, 1.96. What x value does this number represent? And that's these 2 things right here. So the x value that represents the lower bound, this marks the critical region right here, is 81.16. The upper bound, the x value that marks the upper bound, is 96.84 right here. This is the confidence interval. So I'll show you how you could here is what the answer would look like. I'll show you on my whiteboard here. This is a perfectly acceptable way of writing the answer. If you were to do this problem, you would say CI, which means confidence interval, is or equals 81.16 through 96.84. 81.16 through 96.84. That's the answer to this problem. Let's go back. So once again, we're taking this critical Z right here, negative 1.96. It marks the critical boundary, the critical region. And we're converting that Z score using this formula right here into the X value that is represented by negative 1.96. The X value that corresponds to negative 1.96 is this. The X value that corresponds to positive 1.96 is this number right here, 96.84. You'll never have to memorize this because we'll give it to you on the test, but you do need to remember how to use this formula to calculate confidence intervals. So based on what I mentioned earlier, the question is do we have a significant effect or not? And the answer is we reject the null hypothesis. Yes, we do have a significant effect. And the reason is because our population mean of 80 does not fall within the confidence interval. If you look at the confidence interval right here, it's 81.16 through 96.84. 80 is not within these numbers. 80 does not fall within the confidence interval. It falls outside the confidence interval. Therefore, we reject the null hypothesis. And I should remind you that this is the exact same decision that we made when we did the hypothesis test technique in chapter 7. We decided to reject the null hypothesis. If you do the confidence interval for the exact same data, you're going to get the exact same decision whether to accept or reject the null hypothesis, because mathematically, confidence intervals give you the exact same decision as the hypothesis technique in chapter 7. The book does not do a great job explaining that, but mathematically what we're doing is really no different than hypothesis tests in chapter 7. So that is all I have to talk about today, and I think we're right out of time. Perfect timing. It's 10:50 on the nose, so you guys can get out of here if you want, because that's all we're going to cover for today. I do believe there is one group that wanted to talk to me at 11 a.m. So whoever that group is, assuming they're from this class, which I believe they are, why don't we just stick around and we'll talk right now. Let's not hang up and come back. Let's just stick around. I'll end the recording. Stop recording.